Hello class, welcome to section 15.4. We move down to normal distribution. We'll continue with the topic on statistics. The normal distribution is a way of visualizing how data is obviously distributed over, how it can be viewed in distribution over the total amount of data that it has, over the possibilities of data. The most common form of this is called a bell curve. Let's go over this. Like I said, it's a symmetric histogram. Largest values typically in the center, decreasing out. Again, like I said, called a bell curve. In your standard normal distribution, the mean, median, and mode are all equal and at the center. And normal distribution, of course, refers to data sets that things happen the way you would expect them to happen. For example, in your average class, tests and quizzes, most people are going to have around a B or a C, the bulk of them will, which is going to be the biggest part of the bell. You're always going to have people who score very high. You're always going to have people who score very low, typically. So bell curves obviously are often used in education. And those are called normal distributions. Usually you have data, the number of data values, or in the case of like a test or quiz, number of students, for a normal distribution is usually over 30. Usually having over 30 will sometimes, in some statistics courses, they will guarantee a normal distribution or a relatively normal distribution. But right now we're just going to assume we're going to be looking only at situations with normal distribution. One of the most important rules is the 6895-99.7 rule. These refer to the amount of data falling between standard deviations on a normal distribution, which we'll get to in a minute. A z-score is how many standard deviations the data item in a normal distribution lies above or below the mean. Percentile items that are less than a data value. For example, the 80th percentile, 80% of data is less than this particular data value. Again, often used in education or ranking systems. For example, if an athlete is in the top 5% of his category, and whatever it may be, that means 95% of the other athletes fall below him or her in this particular category. So you'd say either the top 5%, or you'd say that athlete is in the 95th percentile. Quartiles are 4 parts, of course, equaling 100% of the distribution, obviously each part containing 25% of the data. And that little symbol on the bottom right is something that didn't get deleted when I was going through this. So you can just ignore that. That's actually how you calculate margin of error, which we will not be doing. So let's take a look at some examples of normal distribution. Of course, it's your standard bell curve. And this is the general normal distribution, where you have 0 in the middle, 1, 2, 3, 1, 2, 3 in each direction. And here's an example of how bell curves work. Bell curves often are formed from bar graphs. And the theory is if you make your bar graph small enough, you adjust the width so that they're very thin, you can eventually get the bell curve starts to form that shape. And you can see that here with these bars. Same thing. The more bars you have, the closer you can come to a perfect bell curve. And here is our 6895-99.7 rule. Right in the center here is where your mean lies. The mean always lies dead center in your standard bell curve. And you see the 1 in each direction, 2 in each direction. That refers to one standard deviation, as you can see. So when you analyze a data set, you look for a mean and you look for a standard deviation. Those are the most commonly used in this kind of analysis. Mean is dead center, and of course if we have normal distribution, we say one standard deviation above and one standard deviation below correspond to 68% of the overall data. and then going one further, 2 and 2, or 2 and negative 2 I should say, corresponds to 95% of all data values between those two markers. And of course you go one more out, you have 99.7% of the amount. Anything beyond that is considered negligible, not really significant. And that formula there for z, that's the formula for the z-score, which we'll get to in a minute. So as you can imagine, there's a generality to this, and this is what it is. That symbol in the middle, if you're not familiar, is referred to as mu, and it's what's used to refer to mean of a data set. So we say mu is the mean of a particular data set. It goes in the center, and the other symbol you see, looks like an O, is referred to as sigma, the lowercase sigma, the Greek letter. That always refers to the standard deviation. So this represents the three areas. Mean plus 1 standard deviation and then mean minus 1 standard deviation give us the first 68%. And this one you see is a little more detailed, 68.26. All you really need to know is 68, 95, 99.7. And as I'm looking even your book, it seems only goes up through, I thought I went through all three. Yeah, here it is. It goes through all three again, 68, 95, 99.7. And the reason I bring that up is some textbooks differ slightly on that. So just another example of normal distribution in heartbeats. As you can imagine, you can break these areas down even further, and if you would like, here is a nice little breakdown of the individual parts. So when I look, let me get my handy dandy marker out here that wants to work. Here is, of course, 1 standard deviation. And we said that going the other way, those two combined areas are 68% about. So obviously if you look at half of them, each one's about 34%. And then if you break that down even further, you can see between the mean and about half of a standard deviation, you have approximately 19.1% of data. Between half and then 1 standard deviation, you have about 15% of the data. And again, this is just a nice little breakdown of all the other areas that you can have. It's a nice reference, especially if you're getting very detailed in a question. So as I continue, now we get to the z-score. Up till now, all this is more analysis once you understand what a normal curve looks like, how much area is in between each standard deviation. But now it's time to apply z-score. Z-score tells us specifically on this grid. So again, on z-score, let me draw it out. On this bottom line here, all these scores, z-scores pinpoint specific spots along there. So specific spots along this lower axis are referred to as z-scores. And this formula is what tells us what those specifically are. Now the formula is needed because when you compile data like this, or it's compiled for you, it usually won't give you 0, 1, 2, 3, -1, -2, -3. It'll put just the mean in with standard deviations, so the numbers would look different. It'll be based off of this. So again, the z-score is what allows us to break everything down to the normal distribution curve. Put it in terms of that normal distribution. You put it in terms from -3 to +3. That's the range for our z-scores. Now, yes, it can go higher. It can ultimately go by the highest 4 or -4. Usually, though, the most meaningful scores are between -3 and 3. So our formula, x minus mu over sigma. Again, mu is our mean, sigma is standard deviation. So for example, suppose the scores on an exam are such that the mean score is 72.5 and the standard deviation is 4.5. What is the z-score for a score of 78? So using our formula, you say 78 minus 72.5 over 4.5, and you do the math to get about 1.22. And that's it. Now, if you look in your book, or online, page 754 is our z-chart. And the significance of the normal distribution is it tells us what percentage of scores, or whatever we're dealing with, lies within certain standard deviations, or now within certain z-scores. So when we mention percentiles, if you're in the 95th percentile, 90th percentile, etc., the z-chart on 754 allows us to determine what specific percentile we're at. So a score 78, we say, is 1.22 standard deviations above the mean. That's what the z-score means. Obviously, if it was negative, it'd be that many standard deviations below the mean. So using the chart, we're going to estimate. So 1.22, if you look on your z column, is the third column over, towards the top, corresponds to 0.38 area. So that means it corresponds to 38.9% of the area under the curve, of the area in that normal distribution right in here. Now the thing is, every z-chart can be a little different. Now, you might notice here that there's only positive values. What that means is it's the same for negative values. The A are the same. The area in the curve is the same, whether it's positive or negative. What that means is, what this chart tells you, and it gives you a good example on page 755. This chart tells you the area between the mean at 0 and that particular standard deviation. So that chart tells you the area from the mean to some standard deviation out here, whatever it may be. The area under the curve. So if it's from here, it's telling you that the area in here corresponds to the chart in your book. Now when you figure out percentiles, obviously you don't want to consider just half of it. You want to consider the whole thing. So to account for that, the way this is set up, because the true z-chart includes everything. To account for this, again, since this is just the right side of the graph, we need to add 0.5. So again, this only refers to half the graph, or 0.5, 50% of the data. So we're going to add 0.5 to get the total area under the curve. Everything to the left of that. So that means we'll get an area of 0.839, or 83.9%. Make sure that's right. Oops, excuse me, 88. My mistake. Good thing I checked. So 88.9% of the data falls to the left of this z-score. So you say you're in the 88th percentile, or you can round it up, say this person was in the 89th percentile of the entire class. And that's how this is interpreted. Some other questions. On the same exam, two students scored 69 and 85. What is the percentage of scores between them? So what we're saying is, on this curve, somewhere the z-score for 85 falls right about here, we'll say, and somewhere the z-score for 69 falls right about there. So we want to know, what is the area between these two data values? That's what that question is asking. How much area is between these two? So we need to figure out what the z-score is for each of these two. 69 gives us negative 0.778. And for 85 gives us 2.778. So according to our little chart here, our nifty little chart, negative 0.778 corresponds to about 28.2%. Now it says here I round to 0.78. And remember, with this chart, whether it's negative or positive, you go by the positive value. It's the same either way. So what this means is, between this z-score and the mean is 28.2% of the data. So again, since it's negative, what that means is since it's negative 0.778, what that means is it's probably right about here. It's saying that 28% of the data is between the median, the mean, and that standard deviation. That's what it's telling us. And I remind you that, so that you know it's based off the mean value, not an overall thing. That's gonna help us solve these problems. And our 2.778 corresponds to about 49.7% of the data. So when we want the area between them, what that means is we're going to add. 49.7 plus 28.2 gives us 77.9, or in this case 77.9% of the scores fall between those two values. So in the context, what this means is between the scores of 69 and 85, between those two student scores, you have almost 78% of all scores between those two. So you can safely say the bulk of the class score between a 69 and an 85. And you can see one of the uses of this kind of analysis. So again, what this means is between the score of 69 and 85, about 78% of all your class, or this class, fell between those two scores. Now, one thing to note is we solved that with adding the data values, because you notice one of the z-scores is positive, one of those negative. These two, for example, are both positive z-scores, 81 and 75. Same question. What's the percentage of scores between those two? Again, notice they're both positive. And the way this z-chart is set up, when you find the corresponding value for each one, 1.888 and 0.555, you have 0.471 and 0.212, so in other words, 47% and 21.2%. Since they're both positive, we subtract the areas, which means we subtract to get 0.259, or 25.9% of the scores lie between an 81, and a 75. So you could estimate a top quarter of the class score between a 75 and 81. Now again, remember, whether or not they're both positive z-scores or both negative z-scores, the way this chart is set up, if they're both positive or both negative, to find the area between the two data values, you subtract. Whereas when one's positive, one's negative, you add the two data values. Finally, let's work backwards. Suppose you scored in the top 10% of the class, or if you want to see if you scored in the top 10%, what would your minimum score be? Of course, 10% score equal to 0.1. Now, since we're talking about percentiles, that's the 90th percentile. So it would be in the top, it means being better than 90% of the class. So 0.9 is what we're actually looking for. So we want to know, look at our chart. This time we're looking at the areas. Where do we get a 0.9? Now again, with this chart, this is only half, so we're actually going to take away 0.5 to get 0.4 or 0.400. So 0.400 is actually what we look for. So again, to review, I want to know if I'm in the top 10%. That means I'm in the 90th percentile. So I want to find 0.9 on my z-chart. Now based on this chart we have in the book, which you'll be allowed to use in tests and quizzes and such, we need to take away 0.5 because it's only half. So what we're actually looking for is 0.4. So if you look in your chart, look for 0.4, and there it is. That corresponds to a z-score of 1.28. So what we've been doing here is we've been trying to find the z-score. We just did. It's 1.28. We want to know what's the score that we have to get on the test to be in that top 10%. So here's the equation we set up. We're working backwards now. So I'm saying I know the z-score. I want to know what x is. So to solve, first thing I'll do is multiply each side by 4.5, which gives me 5.76 equals x minus 72.5. Again, continue to solve for x, and I'll get 78.26. So this means I need to have scored at least a 78.26% on my exam to be considered the top 10% of the class for this particular test. And the same works with any problem like this. In other words, if you're given the z-score, or you're asked to find what individual score or data value do I need to be in this particular percentile, or the top whatever percent, this is the way you do it. You use your chart to identify the z-score and work backwards. Finally, to show you some other parts of normal distribution, these are skewed graphs. So just by comparison, your standard bell curve, graphs like this, skewed to the left, skewed to the right, means they kind of point in those directions. And just some examples. Something a little extra I just wanted you to see. Some examples of skewed graphs. So they're left skewed, right skewed, and that's it. This concludes the section for 15.4. As always, if you have any questions, feel free to contact me, and have a good day.